Imagine standing outside on a perfectly clear moonless night. You know, you've driven hours away from the light pollution of the city.
Oh, out to the absolute middle of nowhere.
Right. And you step out of your car, your eyes finally adjust to the dark, and you look up at this absolutely massive, glittering canopy.
This wall-to-wall stars.
Exactly. You are staring at billions upon billions of stars, and standing there, armed with the sheer mathematical certainty that, well, humanity simply cannot be an isolated accident in all this vastness, you listen.
Yeah.
You wait for a signal, a sign, a whisper. But instead, you are met with absolute deafening silence.
It's a very specific kind of quiet, isn't it? I mean, it goes beyond just the absence of acoustic noise. It is the profound absence of expected company.
Expected company. I like that.
Yeah, because when we look up at the Milky Way, given literally everything we know about chemistry and physics, the universe should be a bustling, chaotic ecosystem of civilizations, and yet it just seems to be holding its breath.
And that eerie, terrifying quiet is exactly why we are here today. I've been digging through this massive stack of sources you sent over for this deep dive, and man, it is intense.
It gets dark pretty quickly.
It really does.
Yeah.
We've got astrophysics research papers, historical transcripts from astrobiology summits, and some deeply unsettling sociological game theory essays.
That's my favorite part, honestly.
Oh, they're terrifying. But the mission for our deep dive today is to really unpack the ultimate cosmic mystery. We're looking at the immense grinding friction between the mathematical optimism that alien life is out there and the empirical, terrifying reality of the great silence.
Right.
So we are going from the birth of stars to the potential self-destruction of advanced civilizations.
And we're going to do it by treating the search for extraterrestrial intelligence, not as, just science fiction, but as a rigorous scientific discipline.
No little green men today.
Right. No. We aren't blindly looking for UFOs. We are actively trying to understand the fundamental laws of how biology and technology actually evolve or fail to evolve in the universe.
Yeah.
So we'll use the Drake equation to sort of map out the probabilities. And then we're going to crash headfirst into the Fermi Paradox to ask the ultimate question, which is, if the math insists they are out there, where is everybody?
It really is the ultimate detective story. And, well, the crime scene is 100,000 light years across.
That's one way to put it, yeah.
So looking through these sources, everything fundamentally points back to a very specific moment in 1961.
Right.
We're at the National Radio Astronomy Observatory in Green Bank, West Virginia, and astronomer Frank Drake organizes the very first scientific meeting on the search for extraterrestrial intelligence.
And the audacity of that meeting, honestly, cannot be overstated.
Because it was fringe, right?
Completely fringe. In 1961, looking for aliens was considered almost career suicide for a serious astronomer. But Drake somehow manages to get an elite group of 10 scientists together, including a very young Carl Sagan.
Oh, wow. Sagan was there.
He was. They even had a neuroscientist there who studied dolphin communication.
Wait, really? Dolphins?
Yeah. Operating on the logic that, if we can't even communicate with another highly intelligent species on our own planet, how on earth are we going to talk to something from Alpha Centauri?
That actually makes perfect sense.
Right. They cheekily called themselves the Order of the Dolphin. But ahead of this meeting, Drake realized a massive logistical problem. He had absolutely no agenda.
I mean, how do you even structure a multi-day conference on a topic where humanity possesses literally zero data?
You don't.
Yeah.
So he sits down and just scribbles out an equation.
And the thing that the sources really hammer home here is a massive misconception that people have today.
Oh, a huge one.
Because the Drake equation was never meant to be a precise calculator, was it?
Not at all. It's not a physics formula where you punch in the mass and velocity and get a definitive answer for how many alien empires exist.
Right.
It was essentially a framework for our ignorance. It was a way to take an impossibly huge, paralyzing existential question and break it down into bite-sized, scientifically measurable components.
Like a to-do list.
Yeah. Exactly like a to-do list. It acts as a cosmic funnel. It starts with the very broad strokes of astrophysics, narrows down into the messy chemistry of biology, and then finally squeezes into the highly unpredictable realm of sociology.
So, the audience listening to this deep dive likely already knows the basic variables, but let's look at how that funnel actually works in practice. Because the transition points are what really matter.
Yeah, the bottlenecks.
Right. You start at the wide end of the funnel with star formation and the fraction of stars with planets. That's pure astrophysics.
Which is relatively easy to measure.
Exactly. Then you narrow down to the number of those planets in the habitable zone, the Goldilocks planets.
And that's where the transition happens. Because once you have a rocky planet with liquid water, the funnel shifts from astrophysics to biology.
It gets infinitely more complicated.
So much more complicated. We have to figure out the fraction of those planets that actually transition from mere chemistry to biology.
Yeah.
Not just sterile, wet rocks, but rocks where self-replicating molecules emerge.
Right, the spark of life.
And then of that subset, the fraction that evolves complex, intelligent life.
Because we don't just want cosmic algae, we want something that can build a radio.
Precisely.
Yeah.
Which is the next bottleneck, the fraction of intelligent life that actually develops the technology to communicate across interstellar space.
And finally, you hit the sociological bottleneck, which is the variable L, the longevity of that civilization.
Right. How long do they keep broadcasting before they either lose interest, run out of resources, or just blow themselves up?
So you multiply all those probabilities together, and you theoretically get the number of detectable civilizations in the galaxy right now.
Theoretically, yes.
Okay, but looking at this mathematically, I have a major problem with it.
Oh, I know where this is going.
I mean, if the first few variables, like star formation, are hard science, but the last few variables, like how long a civilization survives, are literally just wild baseline guesses. Doesn't that make the final number completely meaningless?
Yeah.
You multiply a known fact by a completely fabricated guess. You just get a guess. It feels like a cosmic obstacle course where we don't even know how high the hurdles are.
Your skepticism is entirely justified there. From a strictly computational standpoint, the final number is almost entirely arbitrary.
Right.
Depending on what biases you bring to those final sociological variables, you can make the Drake equation spit out a result of one meaning Earth is entirely alone, or you can make it spit out 100 million.
Which is a huge spread.
It's a useless spread.
Yeah.
But the utility of the equation isn't the final number. The utility is that it gives astrobiology that to-do list we talked about.
Okay.
It isolates the variables so that different branches of science know exactly what to study. It tells the astronomers to go find planets. It tells the biologists to study extremophiles. It tells the sociologists to study civilizational collapse.
So it's a roadmap for the exact things we don't know. And what makes reading through this stack of modern research so incredibly thrilling is that we aren't stuck in 1961 anymore. We've actually started filling in the blanks on the left side of that equation.
We really have. We have fully entered what astrobiologists are calling the Age of Optimism.
The Age of Optimism. I love that.
It's an exciting time. Think about the astronomical baseline in Drake's time.
Yeah.
In the early 60s, we didn't definitively know if a single other star in the entire universe had planets.
Not a single one.
Not one. It was a mathematically reasonable assumption, but we lacked the empirical proof.
Until the exoplanet revolution.
Exactly.
And specifically, reading the literature on the Kepler Space Telescope, the methodology is just mind-blowing.
The transit method. It is an absolute triumph of engineering.
It really is.
To find these planets, Kepler didn't actually see them in the traditional sense.
Yeah.
It basically stared at a single patch of the Milky Way, monitoring the brightness of about 150,000 stars simultaneously.
Wow.
And it was just looking for microscopic dips in their light output.
It's the analogy from the papers, right? The idea of staring at a lighthouse from 100 miles away and trying to measure the minuscule dimming of the beam when a fruit fly flies in front of the bulb.
That's the exact analogy.
It's absurd that we can measure that. But because we can, our understanding of the universe has radically shifted. We now know that the rate of star formation in our galaxy is a steady 1 to 3 stars per year.
Which fills in that first variable perfectly.
Right. But the real game changer is that planets are the rule, not the exception.
Yes. The statistical extrapolation from Kepler's data suggests there are actually more planets than stars in the Milky Way.
That's crazy.
And when we look at the variable for potentially habitable planets, the numbers are simply staggering. Current estimates suggest there could be up to 40 billion Earth-sized planets orbiting in the habitable zones of their host stars within our galaxy alone.
40 billion, that number just completely breaks my brain.
It's hard to fathom.
40 billion potential Earths sitting at the exact right distance from their suns so that water doesn't boil off into steam and doesn't freeze into a glacier. It's just, they're spinning out there in the dark, waiting.
And it's not just Earth-like planets around sun-like stars. A huge portion of these are orbiting red dwarfs. Stars that are smaller and cooler than our sun, but vastly more numerous.
And they live a long time, right?
Incredibly long-lived. A red dwarf can burn for trillions of years, offering an unimaginably long window for biology to figure things out.
So because the left side of the equation, the astrophysics side, is yielding these massive, highly optimistic numbers, it's driving a massive influx of modern search efforts. We're aggressively hunting for the communicators.
Exactly. Look at the sheer scale of the instruments we are building today. Have you seen the FAST telescope in China?
The 500-meter aperture spherical radio telescope.
Yes. It is built into a massive natural sinkhole.
It looks like something out of a James Bond movie.
It really does. It's the most sensitive radio telescope ever constructed. And it is actively sweeping the cosmos, looking for anomalies.
But I want to dig into how that actually works based on the notes here. Because space is loud, right?
Very loud.
You've got stars, quasars, supernovas, they all blast out radio waves. So how do you distinguish between a natural cosmic event and, an alien podcast?
Well, the key is the bandwidth. Natural astrophysical phenomena act like broadband noise. They smear their energy across a huge range of frequencies, kind of like static on an untuned television.
Okay, that makes sense.
But a technological signal, like an intentional transmission, would likely be narrowband. All the energy is tightly compressed into a very specific narrow frequency.
Because that's more efficient.
Exactly. Nature just doesn't produce narrowband radio signals. If FAST detects a sharp, distinct spike at a specific frequency, especially one that shifts slightly due to the Doppler effect of a rotating planet, that is the literal fingerprint of technology.
And we're even getting more sophisticated than just waiting for a phone call, right? The astrobiology papers in our source stack outline a massive paradigm shift.
Yes, the search for biosignatures.
Right. We are tweaking the Drake equation. Instead of relying on the hope that aliens happen to be aiming a radio dish directly at us at this exact moment in cosmic history, we're looking at the chemical exhaust of the planets themselves.
This is a crucial evolution in our strategy. We are using spectroscopy to analyze the light passing through the atmospheres of these distant exoplanets. We're looking for chemical disequilibrium.
Explain the mechanics of that, because the chemistry is fascinating.
Sure. So if you look at a dead planet like Mars or Venus, the atmospheric chemistry has reached an equilibrium. The gases have reacted with each other as much as they can, and they just sit there perfectly stable.
Nothing new is happening.
Right. But Earth's atmosphere is in a constant state of chemical chaos. We have large amounts of oxygen and large amounts of methane coexisting.
And those two gases absolutely hate each other, right? They react and destroy each other quickly.
Exactly. If you have methane and oxygen in the same atmosphere, the methane should disappear in a geological blink of an eye.
Right.
The only way both can exist simultaneously in large quantities is if something is actively continuously pumping them out.
And on Earth, that something is the biosphere.
Yes. Plants pump out the oxygen, and microbes, including the ones in the stomachs of cows, honestly pump out the methane.
Oh, wow.
So if we point the James Webb Space Telescope at one of those 40 billion exoplanets and see oxygen and methane sitting together in the atmosphere, it's the smoking gun of a living biosphere.
So let's bring this all back to the math. You take these modern scientifically backed numbers, billions of stars, tens of billions of habitable planets.
Yeah.
Even if you apply incredibly pessimistic odds to the biological variables, even if you assume that life is a 1 in a million freak accident, you still end up with a staggering result. The math absolutely insists that there should be millions of potential civilizations out there.
The galaxy should be a bustling, crowded metropolis.
And that optimistic math leads us directly into a brutal, terrifying collision with reality.
It really does.
If the galaxy is a bustling metropolis bursting with life, with ancient civilizations that have had billions of years to evolve, why is our radio completely silent?
Why is there no evidence?
Exactly.
Yeah.
Which brings us to the summer of 1950, Los Alamos National Laboratory in New Mexico. It is lunchtime.
Very famous lunch.
Very famous. And the legendary physicist Enrico Fermi is walking to the Fuller Lodge with 3 of his colleagues, Edward Teller, Emil Konopinski, and Herbert York.
And these are not just any scientists. These are the architects of the atomic age, men who deal in the fundamental forces of the universe on a daily basis.
Right. And as they're walking, they are having a very casual conversation about a recent influx of flying saucer reports in the news, and they start debating the actual physics of faster-than-light travel.
Just casual nerd talk.
Exactly. They sit down, they order lunch, the conversation naturally drifts away from aliens and onto other mundane topics. And suddenly, completely out of nowhere, Fermi just stops eating and blurts out, Where is everybody?
And the brilliance of that moment is that everyone at the table immediately knew exactly what he was talking about.
He wasn't wondering where the waiter went.
No. Fermi was famous for his ability to do incredibly rapid, complex estimates in his head, what we now actually call Fermi problems.
Right.
So while they were eating, he had been silently crunching the numbers on the probability of Earth-like planets, the rate at which life should emerge, and the timeline of technological advancement.
And the numbers he crunched formed the chilling logic of the Fermi Paradox. Let's look at the actual timeline of the universe here, because this is what makes it so unnerving.
Yeah, let's break down the timescales.
The Milky Way galaxy is over 13 billion years old. Our sun is a latecomer. It's only about 4.6 billion years old.
Which means there are billions of stars out there that are billions of years older than our solar system.
If Earth-like planets are typical, and life evolves in a somewhat standard time frame, intelligent life could have easily evolved on a planet a billion years before humans even figured out how to use a sharp rock.
A billion years.
A billion years. Think about what humanity has achieved in just the last 100 years. We went from horse-drawn carriages to landing a rover on Mars. A billion years of a technological head start is practically indistinguishable from magic.
And that head start completely negates the space is too big argument that you always hear.
Right, the idea that they're just too far away to reach us.
Exactly. Even if a civilization never discovers warp drive or wormholes, even if they're strictly bound by the known laws of physics and restricted to slow, sublight speed ships, a determined civilization could still colonize the entire galaxy.
How does that math work? Because the galaxy is 100,000 light years across. That's massive.
It worked through exponential growth and self-replicating von Neumann probes.
Okay, walk me through that.
Imagine a civilization builds a fleet of automated robotic probes and sends them to the nearest stars at just 10% the speed of light. It takes a few decades to get there. Once the probe arrives, it mines the local asteroids, builds a replica of itself, and builds a copy of the original probe.
Okay.
Now you have two probes. They move to the next stars, mine, and replicate. 2 becomes 4, 4 becomes 8, 8 becomes 16.
It's like a cosmic viral infection.
Precisely. Even at incredibly slow speeds, pausing to mine and build at every single stop, this wave of exponential replication would sweep across every single star system in the Milky Way in roughly a few million years.
And a few million years is nothing.
It's a rounding error in geology.
By all logical mathematical rights, the Earth should have already been visited. The galaxy should be fully colonized.
We should look through our telescopes and see their massive engineering projects.
Right, like Dyson spheres capturing the entirety of a star's energy output, or the chemical trails of their industrial mining on asteroids, or at the very least, we should trip over a dormant, ancient robotic probe buried on the dark side of the moon.
But we see absolutely nothing. Zero.
The paradox is the glaring, deafening discrepancy between the incredibly high probability of extraterrestrial civilizations and the absolute total lack of empirical evidence for their existence.
It's maddening.
Okay, hold on. I have to challenge this core assumption because I see this in the game theory papers too.
Maybe.
Isn't it incredibly arrogant of us to just assume that an alien species would act like 16th century European imperialists?
Yeah.
I mean, we are projecting our own human aggressive expansionist tendencies onto completely alien minds. What if they reach a point of technological enlightenment and they realize expanding is just a waste of energy?
They just stay put.
Yeah, they just want to stay on their home world, create incredible art, read poetry, and leave the rest of the universe alone.
It is a comforting thought. And honestly, a very common objection. But from a sociological and biological standpoint, it suffers from a fatal flaw known as the uniformity of motive.
Uniformity of motive.
You are absolutely right that some alien civilizations might choose a path of peaceful isolation. Some species might be inherently non-expansionist due to their specific evolutionary history.
Right.
But the scale of the universe is the problem here.
Because if the Drake equation yields millions of civilizations, you need an explanation that applies to every single one of them.
Exactly. If there are millions of civilizations out there, it doesn't matter if 99.9% of them decide to stay home and read poetry.
You just need one.
All it takes is for one single civilization, or not even a whole civilization, just one rogue faction, one alien Elon Musk with a cult following and a shipyard to decide to expand.
Oh, man.
Once that single expansionist entity begins the von Neumann replication process, they inherit the galaxy. Expansionist traits are evolutionarily favored. Those who spread out survive. Those who stay put eventually fall victim to a supernova or an asteroid.
Wow, so to explain the Great Silence, you cannot rely on an alien psychological preference.
No, you need a universal, unbreakable rule that stops everyone without a single exception.
So if they haven't colonized the galaxy and they haven't sent probes and our radios are dead silent, something physical must be stopping them, something lethal, every single time.
Yes.
And that realization brings us to the most terrifying concept in this entire stack of research, Robin Hansen's concept of the Great Filter.
Formulated in the late 1990s, the Great Filter hypothesis is a direct, brutal answer to the Fermi Paradox.
Brutal is the right word.
It posits that somewhere along the evolutionary timeline, from dead, inanimate chemicals to a galaxy-spanning technological empire, there is a step, a barrier, that is statistically almost impossible to pass.
So the universe is basically a cosmic sieve, and the holes are incredibly tiny. It is actively weeding out life. And the most urgent question for astrobiology today is, where exactly is the filter? Is it in our evolutionary past, or is it waiting for us in our technological future? Let's look at the optimistic take first. Let's assume humanity is incredibly lucky and the filter is completely behind us.
If the filter is behind us, it implies that the very early steps of the Drake equation are much, much harder than we assume.
Like getting life started in the first place.
Right. Perhaps the near impossible step was a biogenesis, the actual origin of life. We still don't know exactly how non-living amino acids organize themselves into self-replicating RNA. It might be a chemical fluke so rare that it only happened once in the observable universe.
And even if simple life is common, the next step up is equally daunting. The leap from simple single-celled prokaryotes like bacteria to complex multicellular eukaryotes.
Oh, that leap is fascinating because it required a biological miracle called endosymbiosis.
Endosymbiosis, right.
Around 2 billion years ago, a large predatory single cell swallowed a smaller bacterium. But instead of digesting it, the smaller cell survived inside the larger one.
It just set up shop in there.
Yeah, it began producing energy for its host. That swallowed bacterium eventually evolved into the mitochondria, the powerhouse of the cell.
Wow.
That immense energy boost is what allowed cells to group together, form specialized tissues, and eventually become complex animals.
Now, that's a wild fluke.
Very wild.
Yeah.
On Earth, life was just single-celled slime for billions of years until that one specific accidental swallowing event happened.
Yeah.
If that's the Great Filter, the galaxy is entirely filled with nothing but cosmic bacterial slime.
Which is pretty lonely, but it leans heavily into what's known as the rare Earth hypothesis. It argues that yes, the Kepler telescope found 40 billion Earth-sized planets, but Earth-sized does not mean Earth-like.
Not at all.
The rare Earth hypothesis points out that our specific planet is bizarrely uniquely blessed with a sequence of cosmic lotteries.
It really is a remarkable sequence of coincidences. For instance, we have Jupiter.
Right, the vacuum cleaner.
Exactly. It's a massive gas giant sitting in the exact right orbit to act as a gravitational vacuum cleaner, sweeping away comets and asteroids that would otherwise constantly sterilize our planet.
And we have our ridiculously oversized moon, which isn't just pretty to look at, it acts as a gravitational anchor.
Crucial for stability.
Right. Without the moon, the Earth's axial tilt would wobble chaotically over time. The poles would occasionally point directly at the sun, boiling the oceans, and then freeze over completely. The moon gives us stable, predictable seasons for billions of years, allowing evolution the uninterrupted time it needs.
And we also have active plate tectonics, which most rocky planets seem to lack. Plate tectonics drive the carbon silicate cycle, acting as a planetary thermostat that regulates our atmosphere and prevents us from turning into a runaway greenhouse hellscape like Venus.
So under this optimistic view, humanity has passed the Great Filter. We are the rare freak accident survivors.
They made it through the sieve.
Exactly. The galaxy is empty because literally no one else had the right combination of moons, gas giants, and mitochondrial accidents to make it this far. We are the first ones to the finish line.
It's an isolating thought, but fundamentally an optimistic one.
Right.
Because it means our future is open.
Right.
But we have to confront the pessimistic take, the true terror of the L variable in the Drake equation.
Okay, here we go. What if the filter is ahead of us? What if making life is easy, making complex animals is easy, making intelligent tool users is easy, but surviving the discovery of advanced technology is virtually impossible?
This is where the sociology becomes truly terrifying. What if the Great Filter is the painful transition from a technologically adolescent civilization to a mature, enduring one?
Like growing pains, but lethal.
Lethal growing pains.
Yeah.
Every civilization must eventually unlock the fundamental forces of nature to grow. They must discover nuclear physics, bioengineering, artificial intelligence.
And the second you unlock those, you are holding a loaded gun to the head of your entire species. I mean, we've barely had nuclear weapons for 80 years, and we've already come within minutes of global annihilation multiple times, usually due to, like, a radar glitch or a miscommunication.
And it might not even be the sudden, dramatic destruction of a nuclear war. The great filter ahead of us could be the slow, grinding, mathematically inevitable collapse caused by resource depletion and climate change.
A slow fade out.
Exactly. As an energy-intensive civilization grows, the laws of thermodynamics dictate that it will generate massive amounts of waste heat and chemical byproducts. It will inevitably have severe feedback effects on its planet's biosphere.
Right.
They might destabilize their homeworld's climate, poison their own oceans, and starve long before they ever figure out how to build a fleet of interstellar colony ships.
Which means if you really think about it, finding evidence of alien life in our solar system would be devastating.
It would be catastrophic.
If we send a rover to Mars and find the fossilized ruins of an ancient Martian civilization, or if we drill into the ice of Europa and find the frozen remains of intelligent squid, that would be the absolute worst news in human history.
It would be a death sentence, because if complex, intelligent life evolved independently right next door on Mars and then went extinct, it completely shatters the rare Earth hypothesis.
Right.
It proves that passing the biological hurdles is easy. It proves that the Great Filter is not behind us.
It's waiting for us in the future. A dead alien civilization is a giant cosmic stop sign. It suggests the universe is a graveyard of species that reached adolescence, discovered the power of the atom or the algorithm, and inevitably destroyed themselves. We are just riding the same conveyor belt toward the exact same meat grinder.
It is a deeply sobering realization. However, we have to explore other explanations that don't rely on inevitable self-destruction.
Oh, please, let's do that.
What if civilizations do survive their adolescence? They learn to live in harmony with their biosphere. They don't blow each other up.
Yeah.
But they are physically, environmentally trapped.
Right. What if they literally cannot build starships no matter how smart they are? I want to pull from the planetary science notes here. We are looking at the water worlds hypothesis.
Yes. Let's revisit that FC variable in the Drake equation, the fraction of civilizations that develop communication technology. We carry a massive terrestrial bias.
We do.
We assume that if a species is intelligent, it will inevitably invent metallurgy, build radios, and launch rockets. But what if the environment where life is most common strictly prohibits all of that?
Look at our own solar system. Earth is the only rocky planet with liquid water on its surface. But liquid water actually isn't rare, it's just mostly hidden.
Right.
We have moons like Jupiter's Europa or Saturn's Enceladus. These are entirely encased in miles of solid ice. But beneath that ice crust, due to the intense gravitational tidal heating, pulling, and squeezing the moons, there are massive global liquid water oceans.
And those subsurface oceans contain more liquid water than all of Earth's oceans combined.
Wow.
And because water is the ultimate universal solvent for biochemistry, and these oceans likely have hydrothermal vents providing energy, astrobiologists consider them prime real estate for life. That's exactly why missions like the Jupiter Icy Moons Explorer are being deployed right now.
They're going out there to look.
Yeah, JUICE is equipped with ice-penetrating radar and magnetometers to map these oceans and look for disruptions in the magnetic fields that might hint at salinity and habitability.
So let's run a thought experiment on this. Imagine life evolves down there in the pitch black around a hydrothermal vent. Over billions of years, it becomes highly complex. Picture a civilization of, like, hyper-intelligent octopuses.
Okay, I love this.
They have massive, complex brains. They could have deep philosophical debates. They could compose intricate symphonies using sonar. They could have an incredibly rich mathematical understanding of fluid dynamics, but they are underwater.
And that is the ultimate barrier.
Yeah.
You cannot spark a fire underwater.
Exactly. And without fire, you are permanently trapped in the Stone Age. You cannot smelt copper or iron. Without smelted metals, you cannot build a battery or a generator or a radio tower. You certainly can't refine rocket fuel.
No.
These brilliant philosophical creatures are entirely cut off from the universe above their ice ceiling. They might not even have a concept of stars or space. To them, the universe is just a sphere of water bounded by impenetrable rock below and impenetrable ice above.
They are living in a planetary prison. They're a thriving, intelligent alien civilization, but F variable, their ability to communicate with us, is an absolute hard zero. They will never broadcast a radio signal, and they will never build a spaceship.
It's incredibly frustrating to think about a galaxy full of trapped geniuses, but it also highlights something really profound about our own situation, which the physics papers touch on regarding the anthropic principle.
The anthropic principle is crucial here. It essentially states that the universe must possess the exact properties that allow the observer to exist, because otherwise there would be no observer to ponder it. We look around and think Earth is normal. But Earth is actually a bizarre boundary condition.
We live on a planet that is roughly 32% exposed continental landmass, with relatively shallow oceans and a thin, transparent atmosphere. We exist right on the razor-thin boundary between the solid Earth, the liquid water, and the gaseous air.
And that highly specific, geologically rare environment is precisely the crucible required for technology.
Yeah, so the fire.
Yes. You need the exposed land and the oxygen-rich atmosphere to harness combustion. You need the gravity to be low enough that chemical rockets can actually reach escape velocity. If Earth were just 50% more massive, our rockets wouldn't be strong enough to leave the atmosphere.
Really? Just 50%?
Yeah. The rocket equation is brutal. And you need a clear, transparent sky to observe the stars, which inspires navigation, mathematics, and orbital mechanics.
So the Waterworld's hypothesis flips the script. It suggests that intelligent life is everywhere, just swimming around in the dark. But the highly specific terrestrial environment needed to build a telescope and ponder the Fermi Paradox is astonishingly rare. We might be the only ones with hands, fire, and a clear view of the sky.
It's a compelling argument. But we must also explore the most unsettling scenario.
More unsettling than being alone.
Yes. What if there are advanced spacefaring civilizations out there? They survived their great filter, they evolved on land, they possess the technology to broadcast across the galaxy, but they are actively, intentionally choosing to remain absolutely silent.
This plunges us into the deeply paranoid sociological theories in our source stack, the dark forest and the zoo hypothesis.
Let's start with the dark forest.
Yeah, this is a game theory concept brilliantly mapped out and popularized by the science fiction author Lou Sixon.
And it applies the prisoner's dilemma to a cosmic scale.
Yeah.
It posits that the universe is indeed full of life, but it operates on a principle of absolute, ruthless, paranoid survival.
The analogy is perfect and terrifying. Imagine a dark forest at night. It seems dead silent. It looks empty, but it is not. The forest is packed with armed hunters, stalking silently on their tiptoes through the trees. Every hunter knows that the forest is full of other unknown hunters.
And in this scenario, communication is not just risky, it is suicidal.
Because it gives away your position.
Exactly. The universe contains finite resources. Any nascent civilization, even one that seems peaceful now, could experience an unpredictable technological explosion and become an existential threat in the future.
And the really crucial mechanic here is the speed of light. Because the distances between stars are so incredibly vast, you can't just call up an alien species and have a quick chat to figure out their intentions. There is a massive time lag.
A huge lag.
If you spot a civilization 1,000 light years away, you are seeing them as they were 1,000 years ago. By the time your friendly hello reaches them and their reply reaches you, thousands of years have passed.
Yeah.
You have no idea what their technology or morality looks like now. They could have turned into hyper-aggressive zealots.
This creates an unbreakable chain of suspicion. You don't know if they are hostile. You don't know if they think you are hostile. You don't know if they think that you think they are hostile.
It's the paranoia loop.
It is. Therefore, the mathematically safest, most rational move for any advanced civilization is to stay perfectly, completely quiet. Conceal your thermal signatures, ban radio broadcasts, and if you detect anyone foolish enough to light a fire or broadcast their location, you must immediately destroy them before they have a chance to destroy you.
So the galaxy is silent because everyone is hiding in the bushes and the loud ones are already dead.
Yeah. It's a horrific way to view the universe.
It really is. But I have to push back on this, relying on that same uniformity of motive argument we used against the peaceful aliens earlier.
Okay, let's hear it.
Enforcing absolute radio silence across an entire global civilization seems practically impossible. Out of billions of individuals on an alien planet, wouldn't someone break the rules?
The rebellious teenager argument.
Right. Wouldn't one rebellious alien teenager build a transmitter in their garage? Or a rogue scientific faction beam a message at a nearby star just to see what happens? All it takes is one leak to blow the cover of the entire species.
It is a very strong counterargument. Totalitarian control over every single radio frequency emitted by a species over thousands of years defies logic. But there is another sociological explanation that enforces a different kind of silence, one imposed from the outside.
Okay.
The zoo hypothesis.
The idea that Earth is basically a cosmic nature reserve?
Precisely. The zoo hypothesis suggests the galaxy is heavily populated, and they are fully aware that we are here, but they have collectively agreed to a strict do-not-touch policy. They are passively observing us, allowing for our natural, independent cultural and biological evolution without any external contamination.
But doesn't that fall apart for the exact same reason? If there are dozens of different alien empires, how do you get all of them to agree to this Galactic Prime Directive? Wouldn't one rogue tourist group decide to land their saucer on the White House lawn just for the thrill of it?
To solve that, we have to look at the founder effect and the mechanics of deep time.
Okay, how does that work?
Think about the timeline we established. The very first civilization in the Milky Way to survive its great filter and achieve interstellar capability would have an unfathomable head start. 1 million, maybe 1 billion years.
They would be the ancient precursors.
Yes, they wouldn't have peers. By the time the second civilization crawled out of the mud, the first civilization would have already mapped every star and asserted complete control over the galaxy's resources. They established the rules.
So it's not an agreement, it's a hegemony.
Exactly. This initial founder civilization creates a galactic hegemony. If they decide that young, developing planets like Earth should be quarantined as ethical sanctuaries or scientific petri dishes, they have the supreme power to enforce it.
And reading the AI theory papers in the stack, they wouldn't even need to patrol the galaxy themselves.
No, they'd automate it.
Right. If this precursor civilization transitioned into an artificial superintelligence, it could easily seed the galaxy with microscopic monitoring probes. It could efficiently and violently intercept any younger, rogue alien faction trying to violate our quarantine, completely invisible to our primitive telescopes.
We would be an ant farm sitting on a desk in a high-security facility, completely oblivious to the room, the researchers, or the security guards around us.
There is one more twist in these sociological papers that I find completely mesmerizing. We keep assuming that an advanced civilization's ultimate goal is to expand outward, to conquer physical space, mine stars, and build Dyson spheres. But what if they shift their focus inward?
The transition from the physical to the digital. It's a fascinating thermodynamic argument.
I can explain the thermodynamics of it.
Well, as technology reaches its absolute pinnacle, manipulating physical matter across the vast, cold, slow distances of interstellar space becomes wildly inefficient and pointless.
So instead of conquering the Milky Way, they conquer inner space. The theory is that a sufficiently advanced species might divest themselves entirely of their physical biological form. They upload their consciousnesses into massive, perfectly efficient computer networks and live immortal lives inside a perfect, simulated metaverse.
If you can write code to create virtual universes with limitless possibilities, unconstrained by the speed of light, gravity, or resource scarcity, why would you ever bother exploring the actual dusty physical cosmos?
But wouldn't we still see their massive computers?
Not necessarily. In computer science, there's something called Landauer's limit.
Landauer's limit?
Yes, which dictates the minimum amount of energy required to erase a bit of information. It essentially means computing creates heat.
Okay.
If you want to run a massive civilization-sized supercomputer at maximum efficiency, you want the ambient temperature to be as close to absolute zero as possible. So these uploaded civilizations might not build glowing, massive structures around stars. They might build dark, dormant computational nodes in the deepest, coldest voids of space. Or they might literally go to sleep.
Wait, go to sleep?
It's called the Estivation hypothesis.
Estivation, like hibernation, but for heat.
Exactly. The current universe is too hot for optimal computing. So they build their servers deep underground, put themselves into a state of hibernation, and set an alarm clock to wake them up 1 trillion years from now when the stars have burned out and the universe is incredibly cold. Then they can run their virtual realities trillions of times faster and more efficiently.
So they are out there, but they are literally just sleeping, waiting for the universe to cool down so they can play the ultimate cosmic video game in peace. They have put the entire physical universe on Do Not Disturb.
It elegantly explains the Great Silence. The physical universe looks empty and dead because the truly advanced minds have migrated to a digital reality we cannot perceive, leaving only the physical ruins and quiet stars behind.
Man. So let's pull all of this together and synthesize this incredible journey. We started with the Drake equation, which acts as this beautiful, optimistic roadmap. It breaks down the cosmos and tells us that the physical ingredients for life, the stars, the rocky planets, the water, are spectacularly abundant.
But then, the Fermi Paradox acts as the brutal empirical check. We look at the sheer age of the galaxy, the mathematical inevitability of exponential colonization, and the deafening silence of our radios.
And to reconcile that friction, we are forced to grapple with terrifying concepts. Great filters wiping out species, civilizations trapped under miles of ice, paranoid hunters hiding in a dark forest, or ancient superintelligences treating us like a zoo exhibit.
It's a lot to take in.
And as we wrap up this deep dive, you might be asking yourself why any of this deeply theoretical astrobiology actually matters to your life today. Why should you care about Drake and Fermi?
It's a fair question.
It matters because looking up at the stars isn't just about finding aliens. It is a massive mirror reflecting our own survival.
The variables in the Drake equation are not abstract math. They are playing out on the nightly news right now. We are currently actively testing our own L variable, our civilizational longevity. Are we going to manage our nuclear arsenals, navigate the creation of artificial intelligence, and stabilize our climate well enough to survive our technological adolescence? Will humanity be the species that passes the great filter?
Or will we become just another silent, failed statistic in a cold, empty equation? The silence of the universe is either a dire warning of our inevitable collapse, or it is an open invitation to expand. Which leads me to one final mind-bending thought for you to mull over, a thought that completely reframes everything we've talked about today.
Oh, this shifts the entire perspective of the paradox.
What if the reason the universe is so deafeningly silent is because we are the first?
The first one's here.
Think about the astrophysics of the early universe. For the first few billion years after the Big Bang, the universe was highly toxic. It's too hot, filled with incredibly violent, massive generation I stars that exploded constantly, flooding galaxies with lethal radiation.
And life requires heavy elements: carbon, oxygen, iron, silicon. But the Big Bang only created hydrogen and helium. Those heavy elements didn't exist.
Right.
They had to be forged inside the cores of stars and then blasted out into space when those stars died. It takes multiple generations of stars living and dying over billions of years just to seed a galaxy with enough heavy metals to form a rocky planet like Earth, let alone the complex chemistry of a biological body.
We might be looking at the universe and assuming we are late to the party. But from a cosmological perspective, the party might have literally just started.
We arrived early.
The universe has only recently cooled, stabilized, and enriched itself enough for complex technological life to actually take hold.
The great filter might just be time itself.
Exactly. So what if there is no ancient precursor alien race waiting in the dark? What if humanity is destined to become the ancient precursor race for the rest of the cosmos?
That's a heavy responsibility.
A billion years from now, we might be the ones enforcing the zoo hypothesis or building the Matryoshka brains. So when you stand outside tonight and you look up at that sky overflowing with billions of stars, don't just feel small and don't just listen to the deafening silence. Realize that maybe, just maybe, the universe is holding its breath, waiting for us to speak first.